Well, in this lecture, we are going to start conditional probability. First of all, we need to understand what do we mean by conditional probability and how it is different from the general concept of probability. So this is a special case of probability in which you impose certain restrictions on your sample space. Normally, in conditional probability, you put some restrictions on your sample space, and the sample space associated with certain restrictions is known as reduced sample space, and the probability associated with the reduced sample space is known as conditional probability. In conditional probability, you are quantifying probability putting some restrictions on your sample space. To understand this, let us take an example. For example, if you are asked what is the probability of getting a 4 when a dice is thrown, so clearly the probability is 1 over 6, right? The probability of each and every dot is 1 over 6. For example, the probability of 1 is 1 over 6, the probability of 2 is 1 over 6, and so on, right? But if there is a restriction is put on your sample space, and the question is such that what is the probability of getting a 4 when a dice is thrown, given that there are only even dots occur in your sample space. Now you can see a restriction has been imposed on your sample space. You have to discard all odd dots from your sample space. Initially, when there was no restriction, your sample space consists of 6 outcomes, but now as you see, when you are putting restriction, you have to discard all odd dots. For example, you have to exclude 1, 3, and 5, and so you are left with 3 outcomes, that is 2, 4, and 6, right? So in the light of such restrictions, if you want to find out the probability of 4, this is known as conditional probability. Definitely your probability restricts from 1 over 6 to 1 over 3. In other words, we can say that the probability has been increased by 50%. Initially, the probability of getting a 4 was 1 over 6, but after imposition of the restriction, the probability has switched to 1 over 3. So this is what the conditional probability is. We can also mathematically explain the notion of conditional probability. For example, so if we are interested in the probability of a certain event A given condition B, then the probability of A given B is denoted by P of A given B and is defined as. So probability of A given B can be defined as probability of A given B. This is equal to probability of A intersection B divided by probability of the condition. Condition is B, so it is to be divided by probability of B. Similarly, if you are interested in the probability of B given condition A, and then it is probability of B given A, and it is equal to the numerator is as it is probability of A intersection B, and this time the condition is A, so it should be divided by the probability of A. So this is the equation which is used to quantify conditional probability. So this is the example, and we will solve it using the above formula. So when a dice is thrown, the sample space consists of how much possible outcomes? The sample space consists of number of outcome in the sample space. This is equal to number of sides of the dice, which is 6, and 1 is the number of dice. Since 1 dice is thrown, so this is 6 to the power 1, and 6 outcomes will occur in the sample space. And if you want to construct the sample space will be 1, 2, 3, 4, 5, and 6. So this is the sample space. Okay, now we are interested in the probability of 4. So let A be the event which represents represents 4. Since in a dice there is only one 4, so that's why you have to report 4 over here. So number of outcomes in A, this is how much? This is equal to, this is 1. Now the condition is given that even dots will occur in the sample space. Let B represent the condition. Let B be the event which shows even dots. So clearly B would account for 3 dots because 2, 4 and 6 are even dots only. A number of outcomes in B, this time this is equal to 3. And this is also the reduced sample space because this sample space has been generated in the light of the given condition. The condition is you have to exclude all odd dots. Okay, you are interested in the probability of 4, right? Which means A, the probability of A, given that even dots occur in the sample space only. This is the condition. So by definition, this is equal to probability of A intersection B divided by probability of the condition, right? And according to the classical definition of probability of A intersection B, this is equal to favorable outcomes of A intersection B, divided by total number of outcomes in the sample space. Similarly, probability of B is favorable outcomes of event B divided by total number of outcomes in the sample space. We already know about number of outcome in B is 3, number of outcome in the sample space is 6. Now we need to know about the number of outcomes in A intersection B. Since we know that A is equal to 4, A contains only one sample point, right? And B contains 3 sample points, which is equal to 2, 4, 6. This implies A intersection B is equal to, the common between A and B is 4 only. So number of outcomes in A intersection B, favorable outcomes of A intersection B is equal to 1 this time. So if you put the values, this is equal to number of outcomes in A intersection B is 1, total number of outcome in the sample space is 6. Similarly, number of outcome in B is 3 and total number of outcomes in S is equal to 6. So this is equal to 1 over 6 into 6 divided by 3. This is cancel out and you are left with 1 over 3. So this is how to quantify conditional probability, and this is how to understand conditional probability from a numerical example. Thank you. Thanks for watching.